News of a star exploding in the night sky. A star called T, capital letter T, Coronae Borealis.
Somewhere in the sky tonight, there is a star you cannot see. It sits quietly in a small, curved constellation, invisible without a telescope, unremarkable to anyone who does not know what it is. But astronomers around the world are watching it every single night, because at any moment tonight, tomorrow, next week, that star is going to explode. And when it does, you will be able to see it with your naked eye for the first time in 80 years. The star is called T Coronae Borealis. Most people have never heard of it. But before this year is over, or the next, there is a real chance it will briefly become one of the brightest stars in the entire night sky. Not because it is growing, but because it is dying over and over again. This is the story of the Blaze Star, and it is already happening. It has been 80 years since T Coronae Borealis last exploded. The year was 1946. The Second World War had just ended. The first computers were being built. And in the constellation of the Northern Crown, a star that no one could normally see suddenly appeared in the night sky, shining as brightly as the North Star. Then, within a few days, it faded. And it vanished again, as if nothing had happened. A 15-year-old schoolboy in Wales named Michael Woodman watched it happen. He wrote a letter to the Astronomer Royal describing what he saw. That letter helped establish a theory that would define the next 80 years of astronomy, the idea that this star explodes on a cycle. Roughly every 80 years, it detonates, and then it rebuilds. And then it detonates again. 80 years have now passed. So, before we talk about what is coming, we need to understand what T Coronae Borealis actually is, because this is not a normal star. T Coronae Borealis is not one star, it is two, a binary system sitting about 3,000 light-years from Earth. To put that in perspective, if you could travel at the speed of light 300,000 kilometers per second, it would still take you 3,000 years to reach it. The light you would see from that explosion left the star before ancient Rome existed. The two stars in this system are completely different from each other. One is a red giant, enormous, bloated, dying star in the late stages of its life, so large that if you placed it where our sun sits, it would extend almost to the orbit of Earth. The other is a white dwarf. Tiny, incredibly dense, the leftover core of a dead star roughly the size of our planet, but with more than the mass of the sun compressed into it. These two objects orbit each other every 228 days. And they have been locked in a slow, catastrophic relationship for longer than human civilization has existed. Here is what that relationship looks like. The red giant is so large and so loosely bound together that its outer layers drift toward the white dwarf like fog drifting across a field. The white dwarf pulls this material in. Slowly, steadily, hydrogen accumulates on its surface. A thin ocean of stolen gas growing deeper every year. For decades, this happens invisibly. But the white dwarf in this system is exceptionally massive, over 1.35 times the mass of our sun, packed into something the size of Earth. That extreme mass means the pressure builds faster. The heat compounds faster. And after roughly 80 years of accumulation, a threshold is crossed. The hydrogen ignites, not in a slow burn, in a thermonuclear detonation across the entire surface of the star simultaneously. In a matter of hours, the white dwarf's brightness increases by a factor of 1,500. A star that was invisible to the human eye blazes to magnitude 2, as bright as Polaris, the North Star, one of the 50 brightest objects in the entire sky. And then, over the following days and weeks, it slowly fades back into darkness. The star itself is not destroyed. That is the remarkable part. Unlike a supernova, which tears a star apart completely, a nova leaves the white dwarf intact. The surface is blasted clean, and then the process begins again. The red giant keeps bleeding. The white dwarf keeps feeding. In another 80 years, it will explode once more. But something changed in 2023. Astronomers who monitor T Coronae Borealis noticed the star beginning to dim. Not from the explosion from a quiet, unusual fading that had been seen once before in the months leading up to the 1946 eruption. In the year before it exploded, the star dropped in brightness slightly, a strange pre-nova dip. And in March 2023, that same dip began again. The AAVSO, the American Association of Variable Star Observers, documented the decline. Professionals at NASA's Goddard Space Flight Center sounded the alert. Based on the measurements, the rate of accretion onto the white dwarf, and the behavior matching 1946 precisely, they predicted the explosion would occur before September 2024. It didn't happen. September came and went. Then the end of 2024. Then March 2025. Then November 2025. Each predicted window opened and closed, and the star has not yet detonated. This is not unusual. In fact, it confirms something humbling about stellar physics. The thermonuclear reactions that trigger a nova are among the most complex phenomena in the universe. We can measure the conditions, we can model the system, we can narrow down the window, but we cannot predict the exact moment any more than you can predict the exact second a match will catch flame. Right now, the best estimates point to the 25th of June, 2026, or possibly the 8th of February, 2027. These dates come from a 2024 paper published by the American Astronomical Society based on a precise calculation. The previous eruptions of T Coronae Borealis appear to be separated by exact multiples of the star's 228-day orbital period. It is elegant mathematics. But the researchers were careful. They offered no physical explanation. The numbers line up. The star will decide. What we do know is this. The star is still in its pre-nova state. The conditions are still building. Every night that passes without an explosion is simply another night of accumulation. The match has not been struck, but the flame is closer than it was yesterday. So, what will you actually see? If you are outside on a clear night when it happens, and if you know where to look, you will watch a new star appear in a constellation that had no bright star before. Corona Borealis is a small, curved arc of stars that sits between Boötes and Hercules in the northern sky. It looks like a backward letter C or a crown, which is exactly what the name means. Right now, that crown has one prominent star, Gemma, also called Alphecca, magnitude 2.2. When T Coronae Borealis erupts, a second equally bright star will appear next to it. Overnight, a star that was not there the evening before. For several days, it will be visible to the naked eye. For about a week, binoculars will reveal it clearly. Then, it will fade. Within 2 weeks, it will be gone again, retreating back below the threshold of human vision for the next 8 decades. But here's what that moment means. When T Coronae Borealis erupts, billions of people will have the chance to look up at the same point in the sky at the same time and witness something that has not been visible since 1946. Something that will not be visible again until the 2100s. Every astronomer on Earth will turn their instruments toward it simultaneously. Space telescopes, ground observatories, amateur cameras mounted on tripods in backyards across the world, all pointing at the same event. And at the center of it all, a dead star the size of a planet, erupting in a flash of thermonuclear fire across 3,000 light-years of space. Now, a question that may have already crossed your mind: should we be worried? The answer is no. But the full answer is more interesting than that. A nova at 3,000 light-years poses no danger to Earth. The energy released is enormous, the equivalent of roughly 100,000 times the energy our sun releases in an entire year, discharged in a matter of days. But distance is a remarkable shield. By the time that light reaches us, it will be nothing more than a point of brightness in the sky. There is no harmful radiation, no shockwave, no debris that will ever reach this solar system. We are perfectly safe. Unless something else happens. The white dwarf in T Coronae Borealis is already massive, over 1.35 solar masses and growing. There is a theoretical upper limit for white dwarfs' 1.4 solar masses, the Chandra-Sekhar limit, named after the physicist who calculated it. If a white dwarf exceeds that mass, gravity overcomes electron pressure. The entire star collapses and then explodes not as a nova, but as a type Ia supernova. An event so powerful it can briefly outshine an entire galaxy. At a distance of 3,000 light-years, a supernova would be extraordinary. It would shine as bright as a crescent moon. It would be visible in daylight, it would rewrite the night sky for months, and at that distance, the radiation could have measurable effects on Earth's atmosphere. But this is not expected. The simulations suggest the white dwarf is gaining mass slowly enough that a runaway collapse is not imminent. The nova cycle will likely continue as it has explosive but survivable, violent but contained, for now. What T Coronae Borealis leaves behind after each eruption is not wreckage. It is a reset, a scorched surface, a thinned companion, a system that starts again from zero. This star has been doing this since before humans could write. The 1,866 eruption was documented by astronomer John Birmingham, the first scientific record. Medieval monks in 1217 recorded an unexplained new star appearing in the northern sky in the same position. If the cycle holds, that could have been T Coronae Borealis firing 700 years before anyone understood what a star even was. And it will fire again after us. The explosion that is coming, whether in 2026 or 2027 or whenever the match finally catches, will be seen by the last people on Earth who can say they were alive when it happened before. Some of them were children in 1946. They watched it once, they may watch it again. And the children who watch it this time will be the last generation to see it with their own eyes for a century. There is something quietly staggering about that. A 3,000-year-old beam of light, crossing the entire distance between a dying star and a pale planet, arriving in the retina of someone standing in a backyard, looking up. The explosion already happened. We just haven't received the news yet. Somewhere in the constellation of the Northern Crown, at a distance that makes the word far feel inadequate, two stars are locked in their slow, ancient orbit. The giant bleeds. The dwarf feeds. The hydrogen deepens. And a clock that started in 1946, wound again by physics older than the solar system, ticks toward a moment that no prediction can pinpoint and no force can prevent. It will happen. It is already happening. The only question left is whether you will be looking up when it does.